You know, usually when you talk about energy infrastructure, your mind goes straight to a purely mechanical world.
Right. You picture massive steel pipes, crushing pressure,
Yeah.
heavy machinery.
Exactly. We always just assume the biggest threats to these colossal offshore structures are physical, like, I don't know, a hurricane.
Or structural failure,
Yeah.
or even just extreme deep sea pressure.
Yeah, exactly. But today we are heading into an invisible, really high stakes war happening miles beneath the ocean's surface. And the enemy isn't mechanical at all. It is entirely biological.
It's a war that literally costs the energy sector billions of dollars a year.
Billions.
Yeah, billions. It creates massive safety hazards, it ruins perfectly good resources, and it's all driven by organisms so small you need a high-powered microscope just to see them.
Which is just wild. So welcome to today's deep dive. We've got our hands on an incredibly detailed scientific study from the September-October 2025 issue of OT magazine.
It's a fascinating piece of research.
It really is. It was authored by experts from Vink Chemicals, and it tackles this massive industry-wide nightmare called biogenic souring.
And they didn't just study the problem, right?
Oh.
They actually put a new chemical weapon to the test.
Right, a biocide called grotan OX. They put it through what basically amounts to a microbial torture chamber, comparing it against the current heavyweights of the industry.
And, the findings in this 2025 study are a major wake-up call for the sector. We're looking at a fundamental failure in how we handle subterranean biology.
Okay, let's unpack this. Our mission for you today is to understand exactly how microscopic organisms can bring giant, multi-billion-dollar industrial assets to their knees.
Which is no small feat.
Not at all. But more importantly, we're going to explore why our current chemical defenses are failing so spectacularly, and how shifting our entire strategy, moving away from trying to simply kill the microbes and instead forcing them into a state of long-term metabolic suppression, might actually be the ultimate game changer.
Yet to do that, we really have to look closely at the mechanisms. We need to understand not just what these microbes are doing, but why they manage to outsmart our best chemical defenses time and time again.
Right. So before we can even look at the chemical solutions tested in the lab, we have to understand the exact nature of this invisible enemy.
The root cause of all this chaos.
Exactly. So the industry term used in the text is reservoir souring, and it's driven completely by microbial activity deep underground.
Specifically, the study focuses on sulfate-reducing prokaryotes, or SRPs, alongside a whole host of other anaerobic bacteria.
And these are extremophiles, right? Like they thrive in environments completely devoid of oxygen.
Thrive is honestly putting it mildly. They completely dominate these environments.
Oh, yeah.
Yeah. In deep injection systems, operators pump massive amounts of water into the reservoir to push the oil out, and that water is just full of sulfates.
Okay.
So these anaerobic bacteria essentially breathe the sulfate, and as they metabolize their food, they exhale a very specific, incredibly dangerous byproduct.
Biogenic hydrogen sulfide.
It's exactly H2S.
And H2S is the real menace here. I mean, if you've ever smelled rotten eggs, you know the scent. But at industrial concentrations, it is a multi-layered threat.
It's a nightmare for operators.
Truly. First, it causes severe, rapid corrosion to physical assets. It actively eats away at the steel, creating these iron sulfide scales that just chew through pipelines.
And it doesn't stop at the metal.
Right. Second, it is highly toxic. It creates massive HS&E, that's health, safety, and environment hazards. A leak of concentrated H2S gas can be instantly lethal to a worker.
Which is terrifying.
It is. And third, it actually dissolves into the crude oil itself, degrading the quality. It ruins the processing economics entirely.
What's fascinating here is the sheer scale of the chain reaction.
Yeah.
You have a microscopic organism breathing sulfate, and the result is a massive steel pipe embrittling and shattering under pressure.
It's crazy.
The microbes are engineering their environment to suit their own metabolism, and in doing so, they're literally dismantling the human infrastructure built around them.
It's like discovering that the weeds in your garden aren't just choking your tomatoes. They are actively spitting a highly toxic, corrosive acid that is melting your garden walls.
That's a great visual.
Like poisoning the soil and ruining the actual vegetables you're trying to grow.
It's a very accurate way to visualize it, and it brings up the central conflict of this entire study.
Right, because the energy sector obviously knows about reservoir souring.
They do. They know H2S is a massive risk. So they pump chemical biocides down into the wells to kill the weeds, so to speak.
But the text points out a massive flaw in that current arsenal. I mean, if we use chemical biocides all the time, why hasn't this been solved?
Well, The authors point directly to the failure of traditional short-term strategies.
Especially in deep injection systems, right, where water has a very long residence time.
Exactly, meaning the water sits or slowly moves through the pipes for months or even years.
Right.
The industry has relied heavily on short-term kill strategies for decades. And the logic seems sound at first glance.
Pump in a highly toxic biocide, achieve a massive microbial body count, and assume the pipe is clean.
Exactly. But the text highlights a very telling case study that proves why this logic is just fundamentally flawed.
Oh, yeah, the offshore water flood system.
Right, they monitored this high-salinity, low-flow offshore system. The operators applied conventional biocides over several months.
And initially, the H2S levels dropped significantly, didn't they?
They did. On paper, that looks like a total victory.
Right, problem solved.
On paper, yes. But within just a few days of that initial drop, the hydrogen sulfide levels didn't just slowly creep back, they surged.
Wow.
Yeah. And the authors explicitly state this is not an isolated incident. This bounce back is a systemic failure of conventional chemistries.
Because they just don't last.
Exactly.
Yeah.
They simply do not persist long enough in the reservoir to offer real remedial capacity. They wash away or they chemically degrade.
I have to ask, though, are these microbes actually getting smarter? Like, are we dealing with an antibiotic resistance situation where they are building immunity to the chemicals? Or is the medicine we're using just washing down the drain too quickly?
It's actually a combination of chemical degradation and basic evolutionary pressure.
Okay, how so?
Well, when you use a short-term, highly toxic chemical, you often only wipe out the weakest, most vulnerable microbes in the outer layers of the community.
Leaving the strongest behind.
You leave the strongest, most resilient bugs behind. And because the chemical dilutes over time in these massive systems, the survivors wake back up in an environment where all their weaker competition is dead.
Oh, wow. So they just take over.
Yeah, they have unhindered access to nutrients, so they multiply exponentially.
So by trying for a quick kill, we are basically clearing the playing field for the worst possible bugs to thrive.
Precisely. Which is why the industry is realizing it desperately needs a paradigm shift.
Right.
Next generation strategies can't just be about dumping a more toxic chemical to get a higher day one body count.
The new goal has to be long-term metabolic inhibition.
Yes. You have to break down the physical structures they hide in or disrupt their quorum sensing.
Which is how bacteria chemically communicate with each other to coordinate their attacks, right?
Exactly. You have to shut down their communication and their metabolism.
So because these traditional chemicals just wear off and let the microbes bounce back, the researchers from Vink Chemicals are needed to find a biocide that actually lasts.
They did.
But you can't exactly test experimental, unproven chemicals in a multi-billion-dollar active offshore pipeline. You could ruin the whole reservoir.
No, absolutely not. The risk is way too high.
So you have to build a test environment. And the laboratory setup they built in the UK is just wild.
The engineering of the test environment is crucial to understanding why the results actually matter. I mean, they couldn't just use a beaker of water.
Right. They built 12 pressurized bioreactors operating in parallel, and they packed these columns with a pre-established sand matrix.
And then populated them with a mature, diverse, sessile oil-field microbial community.
Sessile meaning they are physically anchored to the sand, not just floating freely in the water, which is exactly how they live down in the actual rock formation.
Exactly. And the parameters they put these bioreactors under were brutal.
Yeah, they ran these columns completely anoxic, meaning zero oxygen, and they pressurized them to 1,000 seg.
Which is immense.
Yeah, for a little context for you listening, the atmospheric pressure you feel walking around right now is about 14.7 psi, so 1,000 psi is crushing depth.
And they kept the temperature at a steady 30 degrees Celsius to perfectly mimic the environment near a downhole wellbore.
So once the physical environment was perfectly simulated, they had to establish the microbial threat.
Right, they had to feed them. During weekly batch injections, they fed the system synthetic seawater spiked with a highly specific carbon diet.
Yeah, they used 120 milligrams per liter of mixed volatile fatty acids, or VFAs. They were incredibly precise with this diet, too.
Very precise.
It was an exact 100 to 10 to 10 ratio of acetate, propionate, and butyrate. And here's where it gets really interesting.
Oh, yeah.
It's like they built a deep-sea Jurassic Park for these microbes. They pressurized it to 1,000 psi, took away all the oxygen, and then deliberately fed them this perfectly tailored, high-energy junk food.
Just to make them as strong, aggressive, and active as possible.
Exactly. All so they could drop a chemical meteor on them to see which one actually wipes them out.
It really is the ultimate stress test.
Yeah.
So in week 5 of the experiment, they dropped those chemical meteors. They dosed the systems at 750 parts per million, comparing 4 different treatments against an untreated control group.
Okay, what were the treatments?
They used 2 current industry incumbents, glutaraldehyde and THPS. They also tested an unnamed confidential in-house candidate, and finally, Vink Chemicals' new biocide, grotan OX.
And the timeline here is what makes this study stand out. They didn't just check the results the next morning.
No, they ran this pressurized, continuous test for 17 weeks.
17 weeks, wow.
That timeline is everything. As we saw with the bounce-back effect in the field, it does not matter who wins on day 1.
Right.
It only matters who is still holding the line on day 100. Over those 17 weeks, they tracked multiple data streams.
Like energy markers, culturable cell counts, volatile fatty acid consumption.
And, of course, the evolution of hydrogen sulfide. They wanted a complete metabolic picture.
All right, so you've locked these superbugs in a pressurized tube, fed them exactly what they want, and dropped the chemical bombs in week 5.
Right.
We hit week 17. The researchers finally opened the biological black box to see what survived. Walk me through the autopsy of these bioreactors, because the results are vastly different depending on the chemical.
They are. Let's start with the control group, which received no biocide.
Let's go.
Unsurprisingly, they thrived. The microbial load expanded exponentially. The molecular data specifically identified hydrocarbon-degrading organisms, like Marinobacter.
So they were acting as the primary hub for the community.
Exactly. They were driving severe souring, and the hydrogen sulfide levels were consistently extremely high.
Okay, so the control did exactly what we expect weeds to do when left alone. But what about the industry standards, the chemicals the energy sector actually relies on today?
This is where the traditional kill strategy completely falls apart.
Tell me.
First, they looked at glutaraldehyde. It did manage to partially reduce the microbial load, but it failed to eliminate key functional species.
So the hydrocarbon degraders persisted.
Yes. By week 17, the H2S recovery in the glutaraldehyde reactor peaked at 4.3 milligrams per liter.
So partial control at best, it knocked them down, but they were already getting back up.
Exactly.
But the results for THPS, the other industry heavyweight, really stopped me in my tracks. What happened there?
The THPS bioreactor was an absolute disaster. The hydrogen sulfide didn't just bounce back, it surged.
Surged how much?
By week 17, H2S peaked at a massive 50.5 milligrams per liter.
Wait, 50.5? That's not a bounce back, that's an explosion.
It is.
If THPS is the industry standard, how on earth is it making the problem 50 times worse than the glutaraldehyde?
It comes down to the chemistry of THPS and the concept of unintended consequences.
Okay, unpack that for me.
THPS is a phosphorus-based compound. When it degrades in a long residence time system, it breaks down. If the initial dose doesn't achieve a total permanent kill, the degraded chemical actually serves as a nutrient source.
You're kidding.
No. The genetic sequencing of that bioreactor showed that the THPS treatment left behind a highly dangerous reservoir-type anaerobic community.
Oh, no.
And it was massively enriched with methanogens and fermenters.
So to go back to our Jurassic Park analogy, we basically dropped a bomb that only killed the mild-mannered herbivores.
Yes.
And then the bomb itself dissolved into raw meat, feeding all the surviving T-Rexes so they could breed exponentially.
That's horrifying, but accurate.
We selectively bred an elite, high-risk squad of anaerobic survivors.
That is exactly what the molecular data proved.
Oh.
By applying a pressure that didn't fully neutralize the threat, the THPS cleared out the weak competition and literally fed the absolute worst offenders.
I mean, is the cure sometimes worse than the disease?
If we connect this to the bigger picture, this highlights why the researchers relied so heavily on advanced molecular diagnostics.
Specifically, qPCR and next-generation sequencing, or NGS.
Yes.
Let's translate those acronyms for a second, because they are crucial to how we understand this failure.
Absolutely. Think of qPCR as counting the number of cars in a parking lot.
Okay.
It tells you the total volume of microbial DNA present.
Right.
NGS, next-generation sequencing, is like reading the license plate and make of every single car. It tells you exactly who survived.
And the NGS data showed that grotan OX, the new biocide, succeeded specifically because it lowered the functional redundancy of the bacteria.
Yes, functional redundancy.
I love this concept. Explain how that works in a microbial community.
Imagine the microbial community as a highly resilient supply chain. If one specific species of bacteria that produces acid dies, but 3 other entirely different species that also produce acid survive, the community as a whole still functions.
Right, the system has backups.
Exactly. That is functional redundancy.
Yeah.
The NGS data proved that glutaraldehyde and THPS just lowered the overall body count.
Leaving the backup intact.
But grotan OX systematically neutralized the functional pathways. It broke the supply chain.
And you can see that total shutdown in the energy marker data. The study tracks something called the adenylate energy charge, or AEC.
AEC is essentially a measurement of the metabolic energy available to the cells.
Right. Think of AEC as the battery life indicator on your smartphone. The glutaraldehyde maybe knocked the battery down to 50%, but it charged back up.
And THPS plugged the phone into a supercharger for the worst bugs.
Exactly. But grotan OX was the only biocide that provided sustained lethal stress. It drained that microbial battery down to 1% and forced them into a state of dying or dormancy.
It kept them in ultimate power-saving mode all the way to week 17.
Which leads to the single most important metric in the entire 17-week study. 0 significant sulfide concentrations were measured from the grotan OX bioreactors.
0. Nothing.
It didn't just kill a percentage and let the rest recover.
No, it held the surviving population in a persistent state of controlled metabolic stress.
They couldn't eat, they couldn't multiply, and they couldn't produce hydrogen sulfide.
It's a massive success.
A 17-week total victory in a pressurized lab is a massive breakthrough. But, a glass tube filled with sand isn't a 50-mile underwater steel pipe.
That's true.
The real-world oil and gas systems present a physical obstacle that a laboratory bioreactor doesn't perfectly capture, and that obstacle is the biofilm shield.
This is a critical point. When we talk about microbiologically influenced corrosion, or MIC, in the field, we are rarely dealing with loose bacteria floating in the water column.
Right.
The bugs that actually destroy the infrastructure live in mature biofilms attached to the steel.
And the source material describes these mature biofilms as complex physical fortresses. They aren't just layers of bacteria.
No, they are made up of waxes, sediments, minerals, and extracellular polymeric substances, or EPS.
It's essentially a sticky, armored slime that the microbes secrete to build a wall around themselves.
And it acts as a physical barrier.
Right.
You can pump the most advanced, highly stable chemical treatment in the world down a pipeline, but if it just washes over the surface of that EPS slime,
it will never reach the active cells embedded underneath.
Exactly.
It's like trying to neutralize a threat hiding inside a reinforced concrete bunker by just spraying the outside of the bunker with a garden hose.
Yes, you have to blow the roof off the bunker first.
Right? And the researchers are very explicit about this in their conclusions.
They are.
To actually capture the incredible value of advanced oil-soluble biocides like grotan OX, operators cannot rely on chemistry alone. They must combine it with physical, mechanical cleaning.
In industry, this often involves pigging the pipeline, basically sending a mechanical device through the pipe to physically scrape the walls.
You have to violently disrupt that biofilm fortress.
Exactly. Once the EPS structure is torn apart and the microbes are exposed, then you apply the advanced biocide.
The mechanical action removes the shield, and the grotan OX forces the newly exposed microbes into that long-term metabolic dormancy.
Add to that, this dual approach is exactly what lays out the next steps for the industry.
Taking this out of the lab and scaling it up into controlled field trials in actual seawater and produced water injection systems.
They really need to prove that scraping the bunker and applying the chemical suppression holds up in the chaotic, massive scale of real-world operations.
It really is the only logical path forward.
It is. If operators want to finally manage the severe operational downtime, the multi-million-dollar flow assurance issues, and the lethal safety hazards plaguing the industry,
they have to address both the physical structure of the biofilm and the biological resilience of the microbes simultaneously.
Exactly.
So what does this all mean for you listening? Why does this deep dive into an obscure 2025 chemical study matter?
It's a fair question.
Because it represents a fundamental philosophical shift in how we handle biological threats on a macro scale.
The old method, the short-term, highly toxic chemical kill, is obsolete.
In fact, as we saw with the THPS data, it's dangerously counterproductive.
Right, it accidentally breeds super survivors, leaving behind elite squads of methanogens that spike toxic gas levels to 50 milligrams per liter.
The future isn't about brute force. It is about long-acting, highly stable metabolic suppression, using highly targeted tools to hit extremophiles at a molecular level.
Removing their functional redundancy.
Right, and forcing them into a lasting dormancy. We aren't just fighting the bugs anymore, we are putting them to sleep and throwing away the alarm clock.
And that concept of prioritizing dormancy over death brings up a truly fascinating, broader scientific question.
Oh, what's that?
If our best new strategy isn't to completely eradicate these resilient hydrocarbon-eating organisms, but rather to trap them in a chemically induced suspended animation for months or even years at a time in these deep injection wells, what happens to that ecosystem over a decade? If a system goes completely offline or the long-term chemistry degrades unexpectedly after 5 years, are we truly diffusing a microscopic bomb, or are we just hitting the snooze button on an incredibly adapted, hungry microbial community?
Oh, wow. That is a wild, slightly terrifying thought to leave off on. A microscopic ticking clock, locked in suspended animation, miles beneath the ocean floor.
It really makes you think.
It does. Thank you so much for joining us on this deep dive into the source material. It is a stark reminder that sometimes the biggest threats to our massive modern world and the most elegant solutions are completely invisible to the naked eye. Keep questioning the systems around you, keep exploring the hidden worlds right under our feet, and we'll catch you on the next deep dive.